Hello dear student, welcome back to the power electronic classes, which is an initiative of TEQIP Faculties. Let's crack the gate. So, welcome back to the second lecture of the series of power electronics module 2, the uncontrolled AC/DC rectifiers. So, let's start the today's lecture. Alright, so let's have some quick revision first. So, till now we have studied in our previous lecture that what are the basic prerequisites for studying this subject, and also we have studied about what are the various steps for determining for analyzing any power electronic circuit or any power electronic converter. So, again let us have some quick recap of that those steps. So, first of all, what are the steps were that first of all we must know that we have to analyze any power electronic converter instant wise, means we have to choose between the instants, and for those instants we analyze the whole circuit or whole converter circuit. Then we have to see that at that particular instant what kind of devices were used. Then we have seen then that at particular instant what is the status of device, that is whether it is forward biased, reverse biased, or in forward blocking mode or in forward conduction mode. It is true for all kind of devices, whether your circuit is containing uncontrolled devices or it is containing controlled devices. Then based on that, based on above 3 points, we have to redraw a modified circuit based on the switching of the devices. Then we have to apply the circuit equations in terms of KCL and KVL, and then we have to see what kind of load has been provided to us. Then we have to draw the waveforms. So, based on these 7 steps, in my previous lecture we have already discussed about single phase half wave uncontrolled rectifier with resistive load. So, now I have also given some question about what is the average value and RMS value of this given circuit. So, I hope you all have done this. So, the average value comes out to be, if for the above circuit, average value comes out to be Vm over pi, and the RMS value comes out to be Vm by 2. Now, let us move forward for other load types. We have already discussed about R load. Now, we are going to cover in this lecture various other types of loads. So, now today's topic is single phase uncontrolled rectifier with pure inductor load. So, when you are talking about a pure inductive load, let us draw the circuit first. Here this is my source value, this is my load voltage, this is my diode voltage, this is source current, this is the reference load current, and this is reference diode current. So, let us start with the waveforms. So, it's just drawing the axis first. So, let us have, this is my source value, zero, pi, 2 pi, 3 pi, 4 pi, 5 pi. Now, let us say that this is my load voltage, and this is my load current. And last one is diode voltage. So, now again applying the same step by step analysis to this. First of all, we have to analyze instant wise. So, when you are talking about the first instant, the first instant is between 0 to pi. When we talk about between 0 to pi, what is the device type? That is diode. Then what is the status of device? The diode is forward biased, diode is on. So, when diode is on, again when we have to redraw the modified circuit, if you redraw the modified circuit, it will be like this. This is source, this is load, diode voltage. So, now again when you apply the, you have not draw the modified circuit, we have drawn. Now apply the circuit equations. So, here again we are seeing that if you write the circuit equations, you will get like this: Vs minus Vd minus V naught equal to 0. Since diode is on and is short circuited, then Vs is equal to V naught, means again the load is in parallel with the source. Then when the load is parallel with the source, obviously the load will follow the source value. So, from that instant from which the load is becoming parallel with the source, from that instant the output will follow the source, means at t equal to 0, omega t equal to 0, it is becoming turn on. So, it will be like this. Alright. Now, if you talk about current, load current. So, since it is a purely inductive circuit, so here we have to apply the circuit principle based on inductor and capacitor. Alright. In my previous lecture also, I have defined that we must know the behavior of any inductor or capacitor in a circuit. So, when we talk about the behavior of inductor, so we have to basically calculate current, load current. Here the source current is there. So, obviously the source current, diode current and inductor load current both all are same. So, now if you write the circuit equations here, what you will get? We know that the current of that inductor voltage is given as V equal to L di by dt. In our particular case, VL inductor voltage is basically V naught and current through inductor is I naught. And also another circuit equation we know about inductor is that inductor current is given as 1 upon L integration over 0 to t VL dt plus I 0 minus, means the initial condition. So, now if you talk about the initial condition and if you are considering that you have just not turned on the circuit, means for the at the starting of the circuit we can take the initial condition as 0. Alright. So, if you are taking the initial condition as 0, then what will be the circuit equation then? It is from I naught equal to 1 upon L integration over 0 to t. See one thing, note down, please note down one thing, I am not drawing further waveforms without analyzing the circuit mathematically. That is what the circuit equation means. So, 0 to t. Now, what is the inductor voltage at this time? So, here VL can be replaced by V naught. So, the inductor voltage at this time is, what is this? It is equal to Vs. You can see here that we have already derived it, that V naught is equals to Vs. So, we can write simply Vs dt plus, since we are considering initial condition as 0, so it is equal to 0, and this can be written as 1 upon L integration 0 to t Vm sin omega t dt. All right. So, now when we write the equations, when we solve it, what you will get I naught as function of time is equal to one upon L, or rather Vm upon omega L cos omega t with negative sign and 0 to t. When you solve it, we will get Vm upon omega L minus cos. Now, here we have to write the means limits of time. All right. So, we can write it like this, minus cos omega t plus cos 0, or you can write it like that, Vm over omega L 1 minus cos omega t. So, now here you can observe that the load current we are getting as Vm upon omega L 1 minus cos omega t. It is for 0 to t. All right. In our case, 0 to t means we are considering 0 to t between these 0 to pi instants. All right. So, when we are considering the 0 to t as between 0 to pi instant, so when you write omega t equal to 0, in that case what will be the load current? The load current will be Im. If you write omega t equal to 0, what you will get? 1 minus 1, 0, means the load current will also be 0. So, that is true. We know that inductor does not allow any instantaneous change of current, and at the starting of the circuit my load current was 0. That is the fact. All right. So, now it is this mathematical expression is proving that. So, now let us move on to some means another limit. When the limit omega t is equals to pi, in that case if you put omega t equal to pi, what you will get? V naught, or not V naught, it is you will get, we will get I naught. I naught t is equals to, or not t, here I naught t equal to 0, since omega t was 0, so here 0, here I naught pi by omega. If you consider this I naught pi by omega, it is Vm upon omega L 1 minus, since we know that cos pi is minus 1, so minus minus plus. So, 1 plus 1 means the I naught value will be 2 Vm upon omega L. So, let us say if the 2 Vm up means at pi instant the value is 2 Vm upon omega L. Let us say this is 2 Vm upon omega L point. All right. So, now we have to know what is the nature of the curve. That is already clear with this equation. What is the nature of the curve? How you have to proceed with the curve, that is already clear here, 1 minus cos omega t. Or if you can write, if you write Vm upon omega L as some constant value, then the curve is written like, if you write a normalized value of the curve, you can write it like 1 minus cos omega t, where Vm upon omega L is just showing some scaling factor. For normalized value we are writing like this. So, if you draw this curve, I hope you are familiar with the curve, it means how we write curves. So, here when we write the curve value, then we know that how we plot the curve. Just I am giving some basic example. We know that cos omega t is drawn like this, where it is maximum value is between oscillating between plus minus 1, and when you talk about minus cos omega t, it will be a mirror image around x axis. So, it will be like this. Sorry, my wave is not so accurate here, but just to make the concept clear, it will be like this. And when you add 1 to it, when you add a constant value of 1 to it, to this waveform, then obviously this minus 1 point will shift to 0, this 0 point will shift to 1, and this peak value of 1 will shift to 2. So, here if you are plotting this curve and at the instant of pi, see here at pi instant it is going to the twice value. So, here if you add these let me make it very clear, just to make the concept clear. Because this curve plotting is very important. If you have problem with this curve plotting, then it will become very difficult. Just like here, see, we know that cosine wave is plotted like this, which oscillates between +1 to -1, and when you take the mirror image of it, the mirror image will be like this. This is pi by 2 instant, this is pi instant, this is 3 pi by 2 instant, this is 2 pi instant. When you plot the mirror image, means minus cos omega t, this is cos omega t, and we will plot minus cos omega t, it will be like this. Like this. So, minus this -1, this is +1. So, this curve is minus cos omega t. Now, you are adding 1 to it. So, when you know that when we add some bias value or when some constant value is added, means let us say this is the constant value which we are adding to it. So, when this constant value is added to it, this curve will shift upward. This curve will shift to upward of the y axis. So, when this curve will shift to upward of the y axis, obviously this -1 point will come to 0, this 0 point will come to 1, and this 1 common point will come to 2, means the curve will be like this. So, this is +1 point, this is +2 point, and this is 0. So, curve will behave like this. It is a sine, sorry, it is a cosine wave, but it will go like this. Alright. So, this is how the curve will be plotted. So, this is the same nature of current. So, here when we try to plot the current, so it is 2 Vm upon omega L, then obviously at pi by 2, when we will calculate at pi by 2, then so we can calculate at pi by 2 also. We will calculate at pi by 2, obviously at pi by 2 this cos omega t will be 0, and at pi by 2 if you calculate pi by 2 omega, it will be Vm upon omega L, just half of this value. So, when we plot it, so let's draw like this. It is a twice value and it is half value. Alright. So, this is 2 Vm upon omega L, this is Vm upon omega L. When you plot it, it will be like this. Cosine wave. Alright. So, from 0 to pi we have already now plotted. Okay. So, now let us talk about another instant. So, we have already gone to the 5th step also, we have analyzed the waveform mathematically. Now, next step is what we have written here, next step is load. So, as per load we have already analyzed it, that the load is purely inductive. So, based on that load we have analyzed mathematically also with equations. So, now next 7th step is to draw the waveform. So, we have drawn the waveform also. So, now if you talk about the diode voltage here, what will be the diode voltage? Since the diode is completely turned on, so the diode voltage will be 0. So, now moving on to the next step, that is from pi to 2 pi, what will be the circuit condition? So, now when we talk about pi to 2 pi, then we will see what is the circuit condition. In that case, the supply is reverse biased. Alright. So, now to determine what is the status of the switch, we have to first determine what is the load current here. Alright, so now again it comes, what is the property of an inductor? Since we are seeing that at the end of pi instant, the inductor has stored some energy, the inductor current has stored some current which is 2 Vm upon omega L, and it is the property of the inductor that it tries to discharge its energy completely. It does not want to hold it. Alright, sometimes it happens, if you might have observed in your homes also, that if you repeatedly turn on and turn off a switch, it creates a spark there. Why it is so? Because of some inductance present there, means due to wire or due to the motor load or due to any inductance, might be stray inductances may be there. Because of that, what happens when you do frequent switching at your home, what happens that the inductor current which is stored there, it does not allow the instantaneous change of current, but as soon as you are trying to break the circuit or make the circuit again, the current happens to change. In that case, whatever energy is stored in the inductor, if it does not get any path to discharge, then it creates an spark. Alright, so here also, if the inductor does not get any separate path to discharge its energy, what will happen if you try to forcefully turn off this switch, there will be immediately a spark. That's why you have seen that whenever you switch off some motor or some inductive load, some kind of spark happens at the switch. Alright, so now here we see this is not a manual switch which we can forcefully turn off. This is a diode, semiconductor switch. It cannot turn off until it gets the favorable condition. Alright, so when we talk about pi to 2 pi instant, what is happening, that inductor is storing some energy across it, and since there is no separate path for discharging its energy, so what will happen when the supply gets reversed, means pi to 2 pi, when the supply gets reverse biased or supply changes its polarity, what happens due to change in polarity, this diode will tend to reverse biased. But when due to this inductor, since inductor does not allow instantaneous change of current, what will happen that this inductor will also reverse its polarities like this. So when this inductor will also reverse its polarities, so its LDI by dt, this LDI by dt will become very high. So because of this high LDI by dt, this diode will forcefully have to remain turned on. So until unless the inductor energy does not discharge fully, till that time the diode will not be able to turn off itself. So another way to turn off is that either we have to provide some other path, but since in our circuit there is no other path, hence due to high LDI by dt of the inductor, this diode has to forcefully remain turned on. So now what will happen here? So diode is again here remains turned on. So you have to see this also while analyzing the power electronic circuit. You have to see what kind of load is given. So based on that load, you have to determine the condition of the switch. So now we have already determined that again the diode is on. So now we have to calculate that till what point the diode will remain turned on. Alright, so it may happen that the inductor may discharge just before 2 pi also. So let's see whether it will discharge or not. So now again we'll write the circuit equations. Next step, that is V naught, sorry not V naught, we have to write I naught. I naught is equals to 1 upon L integration over 0 to T V naught dt, where V naught I naught are inductor voltage and inductor current, plus IL0 minus. Again, now again the switches, since the switching operation has again happened, so you might know that we show the prior to what switching operation, whatever the condition of the circuit is there, that is called initial condition. So now again at pi instant switching has taken place, so that's why we are considering prior to pi instant everything as initial condition. So now this limit 0 to t we are talking about for instance pi to 2 pi. So now here if you see what is happening here, now let's solve the equation. 1 upon L integration 0 to t V naught is equals to Vs Vm sin omega t. Why Va naught is equals to Vs? We can already see that, because since the diode is on, again the load is in parallel with the source. So, when the load is in parallel with the source, then it is Vm sin omega t, but here the Vm sin omega t is some negative value, alright. So, plus now we have got some initial condition. What is the initial condition? That is 2 Vm upon omega L. So, now let us solve it. We will get minus Vm upon L minus cos omega t 0 to t plus 2 Vm upon omega L. When you solve it, we will get minus Vm upon omega L 1 minus cos t 1 minus cos t plus 2 Vm upon omega L. This is for the instant between pi to 2 pi. Now, again we have to put the values. So, now when you put I naught pi, means when you put omega t is equals to pi instant, at that what will be the value of I naught pi by omega? That value will be minus Vm upon omega L 1 minus cos pi is minus 1. So, minus minus plus some mistake happened here, I think. Oh yes, here. Oh yes, sorry, here the curve is Vm sin omega t. Yes. Oh sorry. So, when you solve it, what we will get here at I naught pi by omega, when we put it here, oh yes, we are talking about 0 to t. So, when you are talking about 0 to t between pi to omega, when you solve it, you will get the same values. It is correct here, you will get the same value. This when you put the value of t, now here please note one thing, here 0 is pi is represented as 0. So, when either I have to shift the waveform or we have to consider it as 0 instant. So, when you calculate it, you will get the same value as 2 Vm upon omega L, and when you put the value of omega t equal to 2 pi instant, what you will get is minus 2 Vm upon omega L plus 2 Vm upon omega L equal to 0. It means that at 2 pi the value is again 0, means now we have to confirm that whether before 2 pi it is 0 or not. So, let us put some other value, let us put let us say omega t equal to pi plus pi by 2, 3 pi by 2. When you put 3 pi by 2, what you will get? I naught 3 pi by 2 omega is equals to minus Vm upon omega L plus 2 Vm upon omega L, means we will get Vm upon omega L, means this point we will get. So, again this is 3 pi by 2. So, what will the value here will be like this. So, we are seeing that the inductor will discharge only at 2 pi, not before that. So, obviously, when till the point the inductor does not discharge itself fully, till that point the value of current will remain the value of diode voltage will remain 0, means the circuit is still remaining turned on. So now, but observe this thing, that between pi to 2 pi, again the load is following the source value, but this time the load voltage is following the negative of the source value. Why it is following negative of the source value? Because during pi to 2 pi the source is already negative. We can see here the source is already negative. So, we will get like this. And again at 2 pi instant, when you again start solving, again the instant for 2 pi to 3 pi, what is happening? The diode is again forward biased, means that inductor will start again charging. When the inductor will start again charging, then you see that the same equations are again applicable, because again the initial condition will become 0, since at 2 pi the initial condition is 0, and again the same conditions will follow and you will get the same waveform. Means for 2 pi to 3 pi, again you will get like this, and the current will again go like this. And when 3 pi to 4 pi comes, again it is repeating this instant of pi to 2 pi, and all these equations are valid here also. So again you will get like this, the load current will be like this. Since load current is like this, so based on the load current you have to draw the load voltage. So the load voltage will be like this, and you are observing that for whole duration of the rectifier, means there is no rectification actually taking place, because of the large inductor value or the pure inductor value. The inductor will not allow diode to turn off at any time. It means that whenever we use pure inductor as a load to any rectifier circuit, actually the rectification never takes place. What happens is that the switch always remains short circuited, and whatever the supply voltage is there, that appears across the load, means no rectification happens. That is why we do not take the pure inductive load for the rectification purposes. So now, based on this analysis, let us take our another load, that is RL type load. So when we take RL type load, let us have the circuit diagram. So in previous circuit, one thing, if you try to follow the average value and RMS value of the load voltage, so here in this case we can see, since there is no rectification taking place, hence the average value of the load voltage will be 0, and RMS value of the load voltage will be Vm by root 2. You have to answer why the RMS value of the load voltage is Vm by root 2 in the comment section. Alright. And if you talk about the rating of the PIV rating of the diode, here the PIV rating of the diode does not matter. Why? Because the diode is always remaining turned on. It is not getting turned off. So here the PIV rating of the diode does not matter, but the only thing which is mattering here is the current rating of the diode. So when you are talking about the current rating of the diode, then you have to take twice the current rating of the diode. Why? Because the diode has to carry a large amount of current, you can see here. So a large value of current rating of diode is required here, just to take care of the current. So now when you go for the RL type load, so we have got this type of circuit. This is our source voltage Vs, this is diode current, this is source current, this is diode voltage plus minus, this is load voltage V naught, and this is load current reference I naught. Sorry. Now one thing, please note that I am marking this load terminal as end terminals like this. I am not marking V naught at any particular value of some element. Alright. Why I am telling this thing? Because there is another concept involved here. What is that concept of a circuit? Is that, say, let's take very simple example. Suppose we have got this RLE circuit and you are putting voltmeter here between A to B. You are putting voltmeter here, all right. So now if some kind of current is flowing through this circuit, any kind of current, I don't know what kind of current, but some kind of current is flowing. Let's connect this circuit here also. This is source value. So now if the current is flowing through this circuit, and if I tell you, or if I ask you what will be the voltage value, then you will simply said that the value of voltmeter will be equal to Vs. The whatever Vs value is there, that Vs value the voltmeter will trace. Why? Because you will see that this AB terminals are in parallel with the source value. So when these we are talking about the voltmeter here, then whatever value of AB terminal combined is there, that value will be traced by this voltmeter. Now you have to means notice one thing here, please don't get confused. We are not talking about only simple resistive voltage, we are not talking about only inductive voltage, or we are not talking about only E battery voltage. We are not taking only these, we are taking the total terminal to terminal, means the combined value of VR plus VL plus E, that will be equal to V. Now let's take another situation like this. And at this time now the circuit is disconnected, and again the same voltmeter is applied at the same place between terminals like this A and B. Now if I tell you what will the voltmeter value, you will simply say that the voltmeter value will be E, because since no current is flowing here, so when the no current is flowing here, so there will be no drop in the resistance, there will be no drop in the inductor. So whatever the E value is there, that will be measured by the voltmeter. Please keep this concept clear in your mind, because when we deal with RLE type of load, and if this concept is not clear, then you will get confused that where is the resistive drop, where is the inductive drop, like that. No, we are not talking about that. Why are we not talking about that? Because we are considering that voltage, whatever load voltage we are measuring, is N to N terminals. All right. So let's discuss about the RL type load. So if you are clear with the pure inductive load and the nature of the inductor, then this type of load becomes very easy to understand. It's not very difficult. So let's draw the circuit first. Oh, I have already drawn the circuit. Let's start with the waveforms. So this is my source voltage. All right. Now this is my load voltage, this is my load current, and this is my diode voltage. Okay. So, now again the first step, we are talking from 0 to pi instant first. So, when we are talking about 0 to pi instant, the switch is diode, means diode is on. When the diode is on and load type is RL, again we have to see, when the L is there, the L will start charging, the inductor will start charging, and due to inductor, when inductor starts charging, it also will discharge itself also. So, let us take, then next step is, when the diode is on, let us means draw the modified circuit. It will be like this. Source voltage, load current, voltage, and here diode current, diode voltage. So, here when you talk about it, so now when the this is like this, or now when first of all, now this is a RL circuit, it is not a pure inductive circuit. So, now again we have to determine what is the nature of the current here. So, when we want to determine what is the nature of the current here, let us write the KVL equations first. So, when we write the KVL equation, we will get Vs is equals to R I naught plus L d I naught by dt, or we can also write like this, Vm sin omega t plus it equal to R I naught plus d L d I naught upon dt. So, here you can see that this is a linear differential equation, non-homogeneous type of first order. So, to solve this kind of equation, linear differential equation, non-homogeneous type of first order, we have to use the method of complementary functions and particular integral, which you have learned in your mathematical courses, that how we will solve this thing. So, when you solve this, we will get two parts of current. First is I naught complementary function part, and second I naught particular integral part, or basically in terms of electrical engineering language, one is natural current and another is forced current. Alright. So, I am not writing the full expression here, I am keeping it as homework for you people to derive this I naught current. Alright. So, in my next lecture, will if your comments will be there to make you understand how that current has come. If you do not know how to derive it, we will derive it also. So, here you know that this complementary function part is, or force function part is a exponentially decaying function. We get this function in the form of a e to the power minus t upon tau, something like that, and this particular integral part is showing the natural frequency of oscillation part, and we get this part as like b e to the power something, some sinusoidal function might be some exponential function might be there, and then some sinusoidal function part like this omega dt plus phi in terms of this. So, when you talk about this complementary function part and particular integral part, you will get this such kind of current. Means the current, if you know in the transient circuit, if it is a purely DC transient, you get the inductor current like this, alright. But since this source is AC, it is not DC. So, what kind of current you will get? It is exponential plus sinusoidal, alright, exponential plus sinusoidal. So, when you get exponential plus sinusoidal behavior, your current function should be like this. Let us make the envelope as exponential and on this if you superimpose sinusoidal like this, sorry, if you have get this sinusoidal function, if you superimpose this exponential behavior here like this, so when you merge these two waves, it will be like this, something like this. So here we can see that here the current will not rise immediately, just as in case of resistance was there. So when the current will not rise immediately, obviously we will not expect a sinusoidal type of current here. So what kind of current we will expect here is kind of exponential plus sinusoidal behavior kind of current. So the current will be something like this. The inductor will start charging like something like this, Alright. Now the question arises, will the inductor continue to charge till pi, or will the inductor charge up to some value and then start discharging like this? So let us say this is curve A and this is curve B. So now we have to know which curve is actually happening. So for that we have to again go to some basics. So we see that there are two functions, one is forced function and one is natural function. So when the current passes here like this, obviously the resistance will have some drop VR. Alright, if you have studied the DC transient part, you might be knowing that what happens then when the resist means why the current saturates there like this. Alright, so when the current flows like this, obviously the resistive voltage will also go like this, the scale may be up or down. So when this kind of thing is happening, so if we say that now since our waveform switching is very fast, alright, so we cannot expect many cycles here. So if we say that the current might be going like this, current is rising like this means the inductor is charging. So if it is going like this, so with the rise of the current, the voltage drop across resistance is also rising. We all agree with this thing. Now see one thing here the voltage, what is the property of sine wave here, that sine wave first before pi by 2 its slope is rising positive, and after pi by 2 its slope is negative falling. So what is happening, since the current is always rising, alright, so till the point the slope of the source voltage is greater than the voltage across resistance or resistive drop, till that point this diode will remain forward biased. Please again note this thing, till the time the source voltage, instantaneous value of source voltage is greater than or equal to the drop across resistance, till that point only the diode will remain forward biased. So here you can see, if we consider this as load current behavior like this, if you see that this is the current behavior, so obviously the resistance drop will also be increasing like this. So at this point you can observe, at this point the drop across resistance becomes equal to the source value, instantaneous value of the source. So now at this point, as soon as the source value crosses this point, let us say if this point is small a, as soon as this source crosses this small a point, what is happening? Now immediately after that the source voltage value is very small, but the load or the drop across resistance is large. So when the drop across resistance is higher than the source value, what will happen? If drop across resistance is greater than the source value, then what will happen? This diode will be reverse biased and the diode will tend to turn off. So, when the diode will tend to turn off, immediately at this point of at A point, what is happening, the inductor, whatever energy stored across inductor is there, it will not allow to the diode to turn off, but what will happen, if the initial polarity of the inductor charging is like this, now the next polarity of the inductor will be like this. So, what will happen, that due to LdI by dt, the diode will remain turn on, the diode will remain on, but what is happening, what if the inductor which is charging prior to point A now start discharging. So, it means that this curve A will be discarded. So, this curve B is correct. That is why when we deal with the RL circuit, we get this kind of wave, the curve B like this. So, let us make it here. So, if this is point A, so till the point A, the peak of the inductor current will go till point A, and after that the inductor will start discharging. Now, when the inductor will discharge, again there is possibility that the inductor may discharge at pi, or the inductor may discharge after pi. If the inductor is discharging at pi, then that is well and good, there is no problem with that. Alright, again the load current will become 0 and circuit will normally operate. But if the inductor discharges after pi, then what analysis is applicable here? The analysis which we have done with the pure inductor case. It means that till the point the inductor does not discharge itself, it will not allow the diode to become turned off. Alright, so we are considering the second case, that inductor is not discharging at pi, but inductor is discharging after pi. We are considering that case. So, if the inductor is discharging after pi, means till point A, the inductor current peak or load current peak will be there, and after that the inductor will discharge. So, this point where the inductor discharges fully is known as beta, where beta is known as extinction angle. Why it is called extinction angle? It was also having some very interesting story, that prior to thyristors there were thyrotron tubes were used, or vacuum tubes were used. So, when vacuum tubes have to be turned off, they also do not turn off immediately. So, there is some kind of arc happens there, or some kind of arc is seen there. So, when the arc is extinguished at some particular point, so extinguishing is there. Alright. So, from that extinguishing of arc, this extinction angle term has came. So, this beta is known as extinction angle. So, in my next lecture we will derive this I naught t and will derive the value of beta also, how this value will get. Alright, in many times GATE has, in the GATE also this question has been asked. So, now let us draw the load voltage based on this. So, we have done the circuit analysis also, alright, mathematical equations are also we have written. So, now if you draw the load voltage, so till the point 0 to pi, the load is connected with the source in parallel. So, and obviously the load will follow the source and the output will be like this. But here you see, since 0 from pi to beta also, the diode is forcefully turned on because of inductor, because inductor is not allowing the diode to turn off until it is it discharges itself. So, till the point beta also the diode will remain turned on. So, from pi to beta we see the source is negative and diode is on. So, the load will follow the negative value of the source. So, we will get like this, and as soon as the inductor current discharges fully, immediately diode will regain its its reverse blocking capability, because with respect to supply the diode is reverse biased. Alright, and again the output voltage will be 0. From beta to 2 pi the output voltage will be 0, and we will talk about the diode voltage. So, from the diode voltage will remain 0 from 0 to beta. Alright, and after that when we talk about diode voltage, what will be the diode voltage at that time? So, if you talk about pi to 2 pi. So, from pi to 2 pi can be break into two instants. pi to beta and beta to 2 pi. So, from pi to beta the diode is on, so therefore, diode voltage is 0, and from beta to pi if you see the diode is off. So, what will be the voltage across it? Whatever. So, if you write the KVL equations, you will get like this: Vs minus Vd minus V naught equal to 0, or Vd equal to Vs minus V naught. Since diode is off, the circuit will be disconnected. So, here V naught will also be 0. So, diode voltage will be equal to Vs, and beta to pi, what is the value of source? So, see, at beta the source has already reached to this point, So, at this point whatever the value of source is there, that will be followed like this. So, again the PIV rating of the diode required is Vm, alright. So, now again when you go for for 2 pi to 3 pi instant, the same 0 to pi analysis is valid here also. So, again the load current will be like this, and diode load voltage will be like this. And the diode voltage will be like this. All right. So, now in this case also you see the time period is 2 pi. So, again you have to put in comment section what is the average output voltage in this case and what is the RMS output voltage in this case. So, for homework, for you have got 3 questions. First of all, you have to calculate that whether the average value is coming to why, that you have to put the give the reason that why with pure inductive load the average value output voltage is 0 and why RMS value of output voltage is Vm by root 2. Second, you have to derive this I naught in the complementary and with the help of complementary function and particular integral. If you are not able to derive it, I will already discuss in my next lecture. And third thing, you have to calculate the RMS value and average value of output voltage for this particular circuit. So, if you like the lecture and give your opinion, your comments on the comment section, and you can ask your queries also through the comment section or through our Telegram group. Till then, thank you very much.